In this video lecture, we're going to be giving you an introduction to functional languages. And Chapter 10 of the Scott textbook provides you with good introduction to functional languages, as do a summary of my notes. If you go down and look at the functional programming notes, those also provide a good introduction. So we're first going to cover the historical origins of functional programming. Then we're going to talk about how functional programming differs from imperative programming. And finally, we're going to talk about one of the primary features used to speed up functional programming, because there's generally a widespread perception, which is kind of true, that functional languages are less efficient than imperative languages. So the historical origins of functional languages go back to the 30s, which is actually when the origins of the imperative model also developed. And the work of Alan Turing led to the imperative model that we know today based on the Turing machine. The work of Alonzo Church, of whom Alan Turing was a student, is what led to the introduction of functional languages. So in the 1930s, a group of people, Alan Turing, Alonzo Church, Stephen Kleene, Emil Post, you may recognize names on theorems from CS 311 and 312. We're looking for developing formalisms that would formalize the notion of an algorithm, or what they thought of as an effective procedure for defining a computation. And they did it based on different formalisms. So Alan Turing did it based on automata, Alonzo Church based on symbolic manipulation, Stephen Kleene based on recursive function definitions, and Emil Post on the basis of combinatorics. The results of these different formalisms led Church to conjecture that any intuitively appealing model of computing would be equally powerful as well. And this conjecture through time has become known as Church's thesis. So when we're talking about an effective procedure, what we're talking about is a distinction between what mathematicians call a constructive proof and a non-constructive proof. So a constructive proof establishes, it actually shows how to obtain a mathematical object with a desired property. So for example, you can give an algorithm for computing the factorial function, whereas a non-constructive proof is one that merely shows that an object must exist, for example, by contradiction. So for example, some of Professor Langston's early work helped show that there were certain problems that had polynomial time solutions, but they were non-constructive because they didn't actually produce algorithms for those problems. They simply showed that a certain class of these algorithms existed. So as you hopefully know from some earlier courses, the Turing machine is a kind of push-down automata using an unbounded storage tape, and basically the automata moves the tape head back and forth across the tape and is able to rewrite portions of the tape. And it's imperative because you're able to modify the state of the tape by writing values of new cells onto the tape, or by adding or deleting cells from the tape. In contrast, Church's model of computing did not have such a notion of being able to modify state. It's something called the Lambda Calculus, although you should not confuse it with continuous calculus. It's something quite different. In fact, is discrete. So it's based on the notion of parameterized expressions. Think of functions, which take parameters, and you can pass different arguments into a function and it will produce different results. So the function is an expression. It takes arguments or parameters, and then based on the values of the parameters returns the results. So the Lambda Calculus was the inspiration for functional programming, and It led to the developments of languages like Lisp, Scheme, FP, ML, Miranda, and Haskell. Lisp is probably the most widely used functional language, widely used commercially. Scheme is a nice crisp subset of Lisp that's used for teaching purposes. FP was kind of a toy language introduced by the developer of Fortran, whose name escapes me at the moment during his Turing Award lecture. ML, Miranda, and Haskell are more research-oriented languages, more modern languages as well, but have not yet caught on as widely in the commercial community. So the key idea behind functional programming is that you're defining the outputs of a program as a mathematical function of the inputs. And a program is simply a top-level function that consists of subfunctions which recursively depend on subfunctions and so on down to the lowest level. And there's no notion of mutable state, so you're not allowed to modify any variables. They're essentially all variables are right once. They're bound either at the time that a function is called through parameters, or within a function you're allowed to set up bindings of variables to values, but you do that at the beginning of the function, and thereafter you're not allowed to change the value of the variable. So you can think of it as all variables must be constant. So there's no side effects. You're in pure functional languages. You have no assignment statements, and it emphasizes recursion rather than iteration. Okay, so before we actually get further into functional languages, probably a good idea to just talk briefly about how they evolved from the Lambda Calculus into the actual forms we see today. And it essentially happened in the 1950s when artificial intelligence researchers were looking both at trying to come up with expert systems for mimicking reasoning and also for game playing. And a lot of the early algorithms use so-called branch and bound techniques, whereby you represented all possible states using a tree. So as an example in chess playing, you might have some series of moves that are start and they're made by white. And then after that, you have counter moves that get made by black. And then you would have counter moves to that that are made by white again. So this tree is actually unbounded in many cases. You might, or it gets very deep with a lot of possibilities. So you don't want to enumerate the entire tree before attempting to branch and bound it. So what would happen is the algorithms would just visit a few nodes at a time and try to assign scores to them. And perhaps the higher the score, then the more likely you are to pursue that particular branch. So here maybe we're most likely to pursue that branch because it's got the highest score. And branch and bound meant you could only make a certain depth search into the tree before you had to come back and maybe consider other possible moves, like say this one that I've just circled. And these algorithms were recursive, and they had to do a lot of manipulation of symbols. And it turned out that functional languages tended to be good for both of these. They were obviously good for recursion. Turned out that often you wanted to use lists to keep track of things, and lists are naturally recursive because they have a recursive definition. You can kind of think of the nil list or the zero element list as the base case, and then you can think of an n+1 element list as simply being an n element list with the nth item either prepended or appended to it. So that's kind of the historical origins of functional languages and their key concepts. So we're going to move on now to what are some of the significant features which set them apart from imperative language. And there's essentially 6 to 7 such features. The first is that in functional languages, functions are first class. And what we mean by that is not only may a function be returned from a function or passed as a parameter to a function, but you can also create a new value, a function as a new value. So you can create functions dynamically and then return these newly created functions from as a return value. And this is something that other languages such as C, C++, and most imperative languages don't allow you to do. So we say in a strict sense that functions are second-class objects in imperative languages because of the inability to create functions as values. And as an example of how powerful it is to be able to create functions on the fly, consider spreadsheets, which in fact are a functional language. So in a spreadsheet, a user types a formula into a cell, and what the interpreter does is it actually creates a function out of that formula that you just typed in. And the arguments to that function are the cells that it depends on. So if you, for example, were to say, let's say in cell A9, perhaps you say A9 is equal to B9 plus C9. Well, now this is a function that depends on B9 and C9. And the reason that I said that a spreadsheet is a functional language is you might have B9 equals, say, 3 times B8, and you might have C9 equals A2 plus B2. And so you're actually, when you evaluate A9, it will recursively call the functions for B9 and C9. The second thing we talk about is higher order functions. And these are functions that take another function as an argument, and possibly that might return a function as well. So a good example of a higher order function is the map function. So map takes a operator or a function, say plus, and perhaps applies it to two different lists, which here we're representing as it being in parentheses. So what this would do is it would apply the plus operator individually to each pairwise elements, producing 3 plus 8, 6 plus 5, and 2 plus 10, or the list 11, 11, and 12. So that's, and map is an example of a higher order function. And we'll get to some of these higher order functions in another lecture on functional languages. But these higher order functions actually are so valuable that they are finding their way into scripting languages like Perl and Python. The next feature of functional languages that set them apart from imperative languages is implicit parametric polymorphism. So in most functional languages, you write a piece of code and the functional language will not require that the variables have declared types. Instead, you might just write something like quicksort, or we'll just say if A less than B, print A else print B. And you won't have to declare the types of either A or B. It will just automatically apply the less than operator if the two operands support the less than operator and have compatible types, or else it will print an error message. So another feature here of functional languages not listed here is that they're typically dynamically typed, and they often don't require you to declare the variables. Okay, the next thing is powerful list facilities, and as talked about on a previous slide, lists have a natural recursive structure, so they are easily handled by recursive procedures. And they are typically a built-in feature of the language, not part of a library as in Java or C++. The next difference is something called structured function returns. And what this simply means is the ability of a function to return an aggregate object, such as an array, a record, a function. So imperative languages have some restrictions typically on what you can return from a function. For example, C and C++ won't allow you to return an array. You can return a pointer to an array, i.e. a pointer to an object on the heap, but you cannot return an array that's a value object on the stack. That's not true in functional languages. In functional languages, you can return all types of aggregate objects from functions, including functions themselves. The next difference is that you have fully general aggregates, including constructors for those aggregates. And you may be thinking, well, wait a minute, you have constructors for classes, I can initialize an array, so what do you mean you don't have fully general aggregates? Well, you typically can only define these constructors at the top level, whereas in functional languages, they provide a way to initialize a structure all at once. So for example, I could write this in Lisp. I'm creating a list, and you can see that I am recursively defining subparts of that list. So I'm defining a sublist. Here's another sublist. Here's another sublist, and within that sublist, I've embedded this sublist. So I can specify the full structure at once. That's not something that I can really do in C or C++. For example, if I had an array, say, let's say I had an array of, say, payroll rec, foo10, I would not be allowed to fully write out the values of the payroll recs here because it's an aggregate structure. So if I wanted to say something like Brad, or put this in Brad, say 10, Sally 8, this is not something that I would be allowed to do in an imperative language like C or C++, this kind of nested all at once specification or initialization of the aggregate, but I can do that in a functional language. And the final feature provided by functional languages is garbage collection. It turns out that they allocate a great many lists. They allocate a lot of temporary variables. Remember, you're not allowed to have side effects. So to mimic side effects, often you're calling a lot of functions, creating a lot of variables, and you have to have an efficient way to deal with all of this. And so they use garbage collection. Another reason they use garbage collection is because they allow you to create these functions in procedures and then return the functions, and the functions are allowed to refer to local variables. So for example, I might have, say, function f, we'll say a, b, and then within function f, let's say we return function g, and let's say it takes a parameter n, and it returns a plus b plus n. Well, an issue here is that I have to retain a and b as part of the so-called closure for G. It's going to be part of the so-called referencing environment for G. If you remember, a referencing environment is simply the set of name value bindings in effect when the expression is evaluated. So we can't throw away the locals A and B, so they're going to have to be allocated off the heap, and a programmer can't really keep track of when it's right to deallocate the variables A and B, but with a garbage collector, that algorithm can. And so garbage collection is really necessary for managing memory in a functional language. When you deal with a functional language, you're going to have to get used to using recursion rather than iteration. So the general idea is shown here, where we have an assignment in an imperative language. We say x equals 0, and then the dot, dot, dot is meant to indicate we're doing some processing. Then we assign expression 1 to x, do some processing. Finally, assign expression 2 to x and do some processing. Well, in a functional language, the way we would simulate those three assignments is with a series of nested function calls. So first of all, we would pass 0 to f1. So f1 would take the parameter x. And the dot, dot, dot that you see right here is the processing that gets done in f1. So the dot, dot, dot ends up returning expression 1 from f1. So now we have in here the return value is expression 1. So now we again have this dot, dot, dot processing producing expression 2. So the return value of f2 is expression 2, and now it gets passed to f3, which does its evaluation, and ultimately we get our result back. So that's kind of an example of how we use nested functions or recursion instead of using assignment. So it's something you have to get used to. And you haven't been brought up to think that way. In fact, at the end of these lectures, I'll kind of have a bit of perspective on functional languages. And I think one of the reasons that it's hard to learn functional languages is we're so used to imperativeness. From the time we were raised as children, we've been told, do this, do that. And so it's very natural to be able to tell a program to do this and do that. That's the imperative way of doing things. It's a lot harder to kind of fit yourself into the mathematician's mindset, which is what you really need for doing functional programming. So we'll come back to that later. Now, sometimes recursion really does a nice job of replacing looping. So here's kind of a rather hard to read set of code. What it's doing is that while I is less than j, it's basically adding the product of I and j to x, and then it is incrementing I and decrementing j. So basically we're going to keep doing this until I and j cross at the value 50. So a little hard to see what's going on perhaps from looking at this imperative code here, but it may be a little easier if you just kind of look at it here. So you're saying if I is less than j, then we return x plus the result of evaluating f on x plus I times j with the value I plus 1 passed in for the new value of I, and j minus 1 passed in for the new value of j. So if you kind of look here, you can see, okay, I plus 1, new value for I. So that's taking care of this assignment right here. And then you see j minus 1 replacing the j, so that takes the place of this assignment right here. And then this x plus I times j replacing this x. So it's just another way of looking at it, but it's a lot tighter code, right? Here you have 2 lines, essentially, whereas up here you have a whole bunch of lines. So that's one example. So what are some natural recursive problems? Well, recurrences are one obvious thing. So for example, factorial. you have 0 factorial is 1, 1 factorial is 1, and n factorial equals n times n minus 1 factorial. So if I wanted to write a factorial function, it'd be pretty easy. I could just essentially say fact of n is if n is equal to 0 or n equals 1, return 1, else return n times fact of n minus 1. So a very simple, it lends itself to a very simple recursive implementation. As another example, we have the greatest common divisor, where you're trying to find the greatest common divisor of A and B. And this is actually the way it's presented mathematically is the definition of the greatest common divisor. So if A equals B, clearly you have the greatest common divisor. It's either A or B. If A is greater than B, then you return the greatest common divisor of A minus B and B. So you basically reduce A by B, or otherwise you reduce B by A. And very simple way of writing it. It would be more complicated probably to write it from an imperative standpoint. You can give it a try. We won't do it here. Some other natural recursions that you're familiar with: tree traversals, graph traversals, like depth first search or breadth first search, naturally written as recursion. But one problem that you probably have already run into with recursion is the fact that it's a lot slower typically than imperative languages, and the reason is all those function calls. Function calls involve an overhead because you have to save register information, you have to create a new stack frame. When the function's finished, you have to pop the stack frame, restore registers. It's can be very, the overhead can be a significant percentage of the function call if the function is relatively small, like it is for factorial, or like it is for something like finding something in a binary search tree. So there's techniques that can speed up recursion. The biggest one is tail recursion, and that tail recursion refers to recursion in which additional computation never follows the recursive call. So if you look back here, this does not tail recursion because after the recursive call to n minus 1 factorial, we still have to multiply the return result by n. But if you look down here in GCD, that is tail recursive because there's no computation that occurs after the recursive call to GCD. So the compiler can do some nifty optimization with stack frames if it knows that a function is tail recursive, and specifically it can reuse the stack frame for the function. So a good compiler can replace the previous definition of GCD with this one. So if A equals B, actually I need here it returns A, else if A is greater than B, we set A to be A minus B, and then we simply go back to start. And if this looks like iteration, essentially that's what it is. You're reusing the same stack frame and you're essentially using iteration, and the same goes for the second one. So a good optimizing compiler can replace your tail recursion with, in effect, a modified form of iteration. Okay, so this doesn't work so well when you don't have tail recursion. So as an example, let's say we had the factorial function n, and remember how it was written. You have if n is equal to 0 or n is equal to 1, return 1, else return n times factorial of n minus 1. So if we tried to somehow convert this to a similar thing, we might have start here, and now we have to kind of have a way of down here replacing n with n minus 1 and then trying to go to start. But you can see there's this issue of what about this n times right here? What exactly is going on there? And it kind of has to come back to it at the end of the function call. But you can see there's a big issue. If somehow we could come back to n, well, and we're reusing the same stack frame, you can see that what happens is n is going to get down to probably the value 1. So when we come back here, that n is 1. Even if we've done some other transformations to this function, we have 1 here, so we probably have 1 times the return value, which is 1, so we're always going to return 1. So that doesn't work too well. So you have to come up with some other technique, and there's a way to do it using something called a continuation. Continuation is basically an argument that contains an intermediate result. So it contains state information. Even though you're not allowed to mutate state, you're allowed to, in effect, update the state and pass it into another function, and then you haven't technically violated the no side effect rule, because you are just pushing that modification or that assignment into another function. So here we have an example where you can see you had to add a continuation argument product to the factorial. And if n equals 0 or 1, we now return the product, which is our intermediate result, and else we return factorial of n minus 1, so n gets updated to n minus 1, and then we have our continuation, which is product times n. And to call this function, what we have to do, we would call it with n and the product initially set to 1. So you can see the base case will get handled okay. If we pass in 1, it will return the product, which is 1. If we pass in 0, all is well, because n will be 0 and will return the product 1. If we say pass in 3, if you do the computation, you'll see we get factorial of 2 and then 1 times 3, so that's going to be our next thing. And then it's going to call factorial with 1, and 3 times 2 is 6. And then because 1 is equal to n, we'll return the product, which is 6. Now, you can debate whether or not this is a nice way to write things. I don't think it is. I think it's essentially taking imperative code, or writing it in an imperative way, and then using this kind of continuation argument to store our state information. I think it ruins the beauty that you get from functional languages, but be that as it may. To give you another example of using continuations, let's take the Fibonacci recurrence relation. We're going to use not the one from the book, but the one Wikipedia uses, because apparently this is the more modern definition of the Fibonacci numbers. So we start with the first Fibonacci number is 0, the second one is 1. After that, we get the next Fibonacci, the nth Fibonacci number, by adding the n minus 1 and n minus 2 ones together. So down here we see a very natural implementation of that recurrence relation. And regrettably, this is exponential. If you would start to write this down, you would find out that there is a lot of repetition that goes in here. So Fibonacci of, say, 4 is really equal to Fibonacci of 3 plus Fibonacci of 2. So now we'll break down the Fibonacci of 3. We'll put that in square brackets. That's really 2 plus Fibonacci of 1 plus Fibonacci of 2, okay, which if we break that down, we get that's the Fibonacci of 2 is a Fibonacci of 1 plus a Fibonacci of 0. Fibonacci of 1 is simply 1. Now we have to break down the Fibonacci of 2, which I'll put in brackets, and that's 1 plus the Fibonacci of 0. And you can see that we're getting a whole bunch. If I'll actually go back and rewrite this as 1, you can see we ended up with 3 calls to Fibonacci of 1 and 2 calls to Fibonacci of 0. And if you were to do this for bigger numbers of n, you would see a lot more duplicated calls. Now there's a cute technique called memoization, which we will get to in another video lecture, that essentially caches the results of function evaluations so that you don't have to repeat them. So once we saw what Fibonacci of 2 is, we would cache it, and when we got to this one, we'd simply reuse the result. But a naive implementation of the Fibonacci of this function is going to lead to an exponential number of calls, and that's what a lot of functional interpreters will do. So in order to make it more efficient, we can think about what's an efficient C implementation. So an efficient C implementation might do it this way. So we're trying to find the nth Fibonacci number, so it builds it up from bottom up. So it starts with F1 being 0 and F2 1, and then it simply starts computing each Fibonacci number till we get up to the nth one. And we know that the next one is going to be F1 plus F2. So then we have to shift F2 into F1, and then we can shift temp into F2, and that leads to a very efficient computation of the Fibonacci number. So rather than going with the top-down approach that we used here, see, this is a top-down approach, we're actually using a bottom-up approach here for this C implementation. And we can use continuations as a way to speed up our functional implementation, basing it off of what we just saw. So instead of going top down, we're actually going to go bottom up. So given a Fibonacci, a number n, we want to find the nth Fibonacci number, we actually define a nested helper function, which we can do in functional languages. They allow nested functions. So we are giving it the previous values of F1 and F2 and the current value of I. And you can see from down here that I will be getting built up. So these are actually, all three of these are continuation arguments because they're all holding computed state. The previous values of F1 and F2 plus how far along we are in the computation. I is like the loop variable I back here. So I is essentially just incrementing itself by 1 each time. So you can see we say if I equals n, we return F2. Otherwise, we return Fibonacci helper, and you can see how we're doing the continuation. F2 is getting set to be, or F1 is now being set to F2. F2, sorry, is being set to be F1 plus F2, and I is getting set to be I plus 1. So in fact, we're doing 3 continuation arguments. And then within fib n, we simply call Fibonacci helper, giving it the first 2 Fibonacci numbers, 0 and 1, and starting our computation with the 0th Fibonacci number. So again, you may or may not like this. I personally hate it because I think it just destroys the elegance of a functional program. But as you become experienced with writing functional programs, this kind of continuation argument passing can become second nature. And the fact that you don't have side effects, it turns out, tends to lead to much less debugging and much faster program development times. Again, that's something we'll get to when we do our perspective on functional programming in the wrap-up lecture. In the next lecture, we're actually going to be talking about some of the evaluation issues that come up with functions, and then another lecture where we review functional programming and also perhaps talk about higher order functions.